anytime we write integral like this, c, versus this just means doing that path backwards, all right? And the natural question is, do you think it changes the answer? No? What is the line integral geometrically? It's the area of that curtain, right? It's the area of the curtain. Now, it shouldn't. You have to think about when we did this. Remember where that square root part came from? Remember the square root part came from looking at this curve on the ground and then doing like a right triangle? And this was dx and this was dy, and then doing Pythagorean? So if I go this way on the curve versus this way on the curve, isn't that always going to be the square root of those two things squared and added? So it doesn't matter which way I go, ds will always be the same, right? But not dx and not dy. If we project onto the planes, then the direction actually matters. Because if I go here, look at the area right here. On this curve, on this thing right here, that curtain, the dx, that area, dx for us is the width of this like rectangle in here, right? Dx is the width, and it's always been positive to us because we've gone from left to right. But what if you go from right to left? Then dx is actually negative, and so the direction will matter. So the conclusion is this. All that matters is this right here. If you were to take and look at the area of the curtain below this function over that curve, whatever that answer is with respect to x, if you change the direction of the path, then it makes the answer opposite in sign. So whatever this was, it switches the sign. Same with respect to y. If you do a line integral with respect to y over c, then you change the direction, negative c, then you're going to change the answer. It's going to change by a sign. The only one that doesn't change is when you do it with respect to arc length. Then, because of the Pythagorean, it doesn't matter. So it's going to be the same answer either way. Okay? You're just going to take that on faith. I tried to geometrically convince you. Next note, path independence. Now this is a different thing. Previously, right, I'm saying, what if you did the path the opposite direction? Now I'm asking you to consider this. If you're given 2 points, right, A and B, we could have different paths, right, going from A to B. We could have that path, C, this one I'm calling C tilde, right? Should we get the same answer? Think about area of curtain. Will that area be the same, you think? Probably not, right? Remember, the surface is on top. You're dropping down. The area of the curtain above this one and the curtain above that one should not be the same. We should get different answers. So here's an example to kind of see if we can't convince ourselves that we get different answers. So we want to find this line integral. Look at that right there. So that's that new notation, right? This is that new notation where we do with respect to x and y separately with an addition between them. So we're going to, this is 2 different problems, not one problem with 2 curves. The first curve we have is the arc of the parabola. Here's the parabola. And it goes from here to here. And then the other is just a line segment. So I'm going to do the parabola first. Okay, let's call that C. All right, perfect example of the parametric that you were asking about earlier. Notice that this is x is a function of y. So what I'm going to do is I'm going to write this. X of t, y of t. I'm going to put, for y of t, I put t. For x of t, I put 4 minus t squared. That will draw me that parabola. Now, I didn't actually draw you the picture. I'll draw it over here. We're going from -5, -3, to the point 0, 2. Yeah, it should be doing something like this, roughly. I'm just going to cut that off because we only want to go from there to there. We want to go from here to here, like that. So how do we do that? What's our restriction on t? So what's the first? Let's go with the second point, 0, 2. We want to end at 0, 2. So we want our x to be 0 and this to be 2. 2, right? 2 should do that. What happens if you plug in 2 here? You get 0, 2 here, you get 2. Do y'all see that that gives me the second point? Now the first point, what do you want your y value to be? Negative 3, right? So how do you make this negative 3? Negative 3. Negative 3, what's negative 3 squared? 9, and then you have 4 minus 9, negative 5. So that works. That takes a little bit of inspection, but you should be able to figure out those two limits. We need some derivatives, don't we? Okay, x prime of t, negative 2t. Y prime, 1. Okay, I think I've got everything. Got the parametric, right? Got the derivatives, got the limits of integration. Let's do this integral. So that's going to be the integral from negative 3 to 2 of y squared. What's y squared for us? T squared. Okay, then times dx. What's dx for us? Negative 2t dt, right? And then plus, let's do a new integral. Negative 3 to 2 of x. What's x for us? 4 minus t squared, and then dy. 1 dt. Pardon me? Wait a minute. Where are you talking about? So this is x, right? And this is dy.
Oh, never mind. Yeah.
Were you thinking ds?
Yeah.
Oh, okay.
I was looking for the y and.
Got you. Got you.
I'm confused. Yeah.
It's this one, right?
Yeah, yeah.
This one right here. Okay, that's it, right?
Yeah.
Now we could put this all into one integral, couldn't we? Like this is just negative 2t cubed, and then this one is just 4 minus t squared. We can put that all into the same integral because they're both going from negative 3 to 2. Let me do that. This will be integral from negative 3 to 2 of negative t cubed plus 4 minus t squared. All of that dt. And I'm going to use the computer to get that answer, and we'll do that in a minute. But is there any question on the setup? That's just the first part. So this is going to give us an answer, right? Now what we're going to do is we're going to do, instead of the parabola connecting those 2 points, we're going to do the line segment connecting those 2 points. We're going to do that on the computer, and we're going to see if we get the same answer. We kind of know we're not going to, but this is just to confirm that, all right? So now let's call this other curve, let's call this the straight line segment. Let's call this one C tilde, just so we know it's different than C. And I need to draw the straight line segment. I'm leaving that one up over there. I need to draw the straight line segment that goes from the point negative 5, negative 3 to the point 0, 2. So let's do it. R of t, right? R naught plus TV. R naught would be where we're starting, plus t times the direction vector from here to here. 5, 5, 5? 5, 5? Yes?
So is this like the projection of the curve onto the plane that we're finding right now?
Is this the projection of the curve?
No, you're showing like a curve and then project it onto like a plane, like the YZ.
No, what this is we have a surface up top, right? And then on the ground we have two different curves. Now this isn't drawn right, but we had the parabola we just did, right? It was a parabola. And so the area, if we plug those points in, we get an area here, right? From that curve up through here. That's the area of that.
Okay.
Now what we're doing is we're looking at a separate curve that doesn't, it's not parabolic, it's a straight line segment like this. And we're going to find, if we plug that in up here, we're going to get something up here, and we're going to drop down, we're going to get the area. And the question is, are they the same area?
Okay.
Right? And what does your instinct tell you? No, right? And it's sometimes it is the same answer, sometimes it isn't. It depends on the curve itself. But this is just to show in general it's not. Do you see the difference geometrically? Okay. All right, so what now? Oh, put them together, right? Put them together. Oops. -5 plus 5t, -3 plus 5t. So we've got our x of t, we've got our y of t. X of t is -5 plus 5t, y of t is -3 plus 5t. Our derivatives are pretty straightforward here, right? 5, 5. And we can set up this integral. Oh, sorry, 0 to 1, yes? 0 to 1 on t? 0 to 1? I didn't state that, but line segment, right? Same idea. So now what we do is we set up the integral. It's going to go integral from 0 to 1 of y squared. So that's -3 plus 5t, that quantity squared, right? That's y squared. dx was 5 dt, right? Plus, I'm going to do this all in one integral, plus what? X, which is -5 plus 5t, times dy, which is 5 again, and then all of this dt. So that one I did together, just all at one time. And then we can figure out what that is, right? Can we save ourselves the time and just trust that if we went onto the computer and got these, we get two different answers? Is that all right with you? I think what's more important is the setup of everything and like where to put everything. So here's the conclusion. If you're given 2 points, A and B, what happens if we choose two different paths connecting them? Does it change the value of the path integral? Answer, in general, the line integral depends on the path. If we change the path, it's likely to change the line integral. There are some conditions which make the value of the line integral independent of the path chosen. And we will be addressing that later on. Okay? So the idea of the line integral that we just did was very easy for me to show you, right? This seems to be a theme in this class, right? It's like first I can show it to you and then we go into a higher dimension and I can't show it to you anymore. Same idea though. Here what we were doing is I said, okay, we got a curve on the ground and then we got this function that creates this curtain. And when I first introduced the idea to you, what I said you could look at, a way you could look at it is if you were given a curve in space and I give you the density at every point, right? I give you some density function at every point, then we can use that to find the mass of this wire, and then we could find the moments in the center of mass and all that stuff, right? The way you can look at the density is by laying this on the ground. There's your curve. And then the density at each point has this value, and that would be the surface up here, and then the total area of this curtain would represent your mass of your wire. So it's like, you don't have to look at this as a curtain. You can look at it as a wire with density, and then this integral would give you the sum of the value of some function at each point, which in this case would be our total mass. So now we want to do line integrals now, but we don't want our line to have to, our curve, we don't want the curve C to have to live on a flat sheet of paper. We want that curve C to be able to live in three-dimensional space. And the problem with that is now your function, right, is now in four-dimensional space. So you can't talk about areas of curtains anymore. But you can still do the same thing. If you have a curve in three-dimensional space, or like a wire, and then you knew the density at each point, then this new integral would represent the total mass. Okay? Now we have slightly different notation and language for this. We call these line integrals in space, meaning like space, like dimensions, right? 3D space. So if we take a smooth curve in three-dimensional space, right, instead of on a plane, we can still find parametric equations, but now we'll have x, y, z, right? A parametric for each one. And then we'll have some restriction on t. And then we could convert this over to a vector function. Remember, vector functions of a single variable like that draw curves in three-dimensional space. So we're going to step away from the parametric notation and go back to the vector notation, which is this. Then we can define the line integral of f along this curve as follows. Line integral, this is the same. Line integral over c, but now it's what? F of x, y, z. This is still ds. It's still arc length. What changes? Nothing. You're going to take the scalar function, you're going to plug in the x, the parametric for x, y, and z respectively. Same thing. Now this changes a little bit because when you do the arc length in three-dimensional space, you have to throw in that third piece, still dt. So everything is just like translating exactly over, isn't it? But then we change the notation just to make your life hell, right? What we do is instead of writing this, when we write this, instead of writing this, look at this new notation. This is it right here. What we're doing is we're saying we have some vector function, right? Some vector function. And the vector function is the x of t, y of t, z of t, respectively, right? These are our parametric equations, x, y, and z. But instead of writing f of, replacing the, go into the f and replace the x with x of t, y with y of t, z with z of t, this is what we'll write instead. F, and inside of it, plug in this vector function. Now this is weird notation, okay? F with this vector function plugged in, what that means is exactly what this notation right here means. You take the x and plug it in for the x, the y, and then the z. It's a strange notation because we're plugging a vector function into a scalar function, which actually doesn't make a whole lot of sense. So it's purely a notational thing that you need to understand. And then, what is this? The magnitude of the derivative. What the hell is this? The magnitude of the derivative of r. Well, here's r, right? What's its derivative? How do you take derivative of a vector function? You just take derivative of each one, okay? And then how do you take the magnitude of that? Square root of the sum of the squares of all those, right? Isn't that what this is? That's exactly what this is. So this is just a condensed notation of that. That's all that is, right? So it's just a more compact, tight formula that represents the exact same thing. All right. And as before, that's with respect to arc length, right? But there are three other versions where you can go just with respect to x, so you'll have an x prime instead of that square root thing, or you'll have a y prime, that's called with respect to y, and then you have this additional one with respect to z. So this is all very much analogous. Is that right? Is that the right word I should be using? Analogous? Means the same thing? All right, and finally, we will see later all three of those together. Some scalar function p of x, y, z with dx, then q of x, y, z with dy, and then some r of x, y, z with dz. And instead of writing that, we will just write one integral symbol with all of this, and it means all three of those added. Let's do an example. Shit, we have 2 line segments, don't we? Which means we have 2 C's. We have a C1 and a C2. All right, let's start with C1. I'm not going to draw it, okay? Because then drawing points in 3-dimensional space kind of sucks, right? So for C1, it's going to, this one right here. This one's going to be the one for C1, and then this one right here is going to be for C2. All right. What vector function, r of t, will draw me the line segment from there to there? So R naught, what's R naught? The origin, 0, 0, 0. Plus t times v, what's the direction vector? 1 to negative 1, right? So this is just, let's condense it all together into one thing. Can we call this R1 of t? That way we don't confuse it with this R when we get it? Okay. This is just t, 2t, minus t. There we go. Do you remember there was a day in here when I gave you 2 points in 3-dimensional space and asked you for the vector between them? And that's just like this trivial little thing now, right? Okay, now let's get C2. C2. All right, we'll call that R2 of t. All right, this is a little different. Where are we starting? 1, 2, negative 1, and we've got t times the direction vector from here to here. So what? 2, 0, 1. 2, 0, 1. And now put those together, we should get, let's see, 1 plus 2t, 2, just 2, and then negative 1 plus t. On both of these, t goes from 0 to 1, right? On both of these, t goes from 0 to 1. Integral time? I think I have everything I need. All right. Starting with the line integral up there, I know I'm going to go from 0 to 1. All right, x squared. Oh, wait, hold on. Time out. I do need to do 2 of these, don't I? So integral over c1 of x squared dx plus y squared dy plus z squared dz plus the line integral over c2 of x squared dx plus y squared dy plus z squared dz. All right, now I can separate the two, right? So this one goes from 0 to 1. Okay, x squared, but we're on c1. So what's x squared for us? So this is, right, this is x, y, and z, right? So x squared is going to be t squared. And then what's dx? I didn't bother taking derivatives because I figured we could do it pretty easily. What's the derivative of that x function? 1. 1 dt, right? Now, do you want me to do another integral, or do you want me to just wait on the dt and put it in the back? Wait on the dt? Okay, so let me do it this way. I'll put 1 here. So that's derivative, okay, plus, all right, what's y squared? 4t squared. dy? 2 dt, right? Plus, what's z squared? Negative t squared, but that'll be t squared, right? And then dz, careful on dz, negative 1. And then all of that dt. Okay, do I need to run through that? X squared dx plus y squared dy plus z squared dz, right? Using this as our x, y, and z respectively. All right, plus, now my second integral, I go from 0 to 1. Okay, now I'm working with this one, right? This one instead. So x squared would be 1 plus 2t squared, right? dx, what's dx? Times 2, okay, plus y squared, 4 times dy, 0, yeah, 0, it's gone. That piece is not going to contribute. And then plus z squared, negative 1 plus t squared times 1, and then all of this dt. X squared dx plus y squared dy plus z squared dz dt. I think that's all doable now, right? It's pretty straightforward. All right. That's it. We're done with line integrals. Line integrals. So you have line integrals in two-dimensional space, which was the area of the curtain, right? When we did line integrals in space, you had the surface. Line integral in two-dimensional space. You had your surface, then your curve was on the ground, and we looked at its area, right? The function up here was a scalar function, wasn't it? F of x, y. And the curve on the ground, we did parametric. Then we went into three-dimensional space. So now our surface isn't a surface anymore. It's in four-dimensional space. But it's a scalar function, f of x, y, z. The curve lives in three-dimensional space. That's going to be very different than what we're about to do. So I just want to make sure you all understand. In all the line integrals we've looked at so far, and everything we've seen, right, when it comes to line integrals, the first one we had was this. And then we could do it with respect to x or just with respect to y. And then we did, oh, sorry, I did not mean to put double. Sorry, line integral. Then we did line integral c of f of x, y, z ds, right? And we had a different notation for this as well. We could also do f of r of t and then times magnitude of r prime of t dt. These two things meant the same exact thing. Seems like, I don't know, what would come next? I mean, naturally, you would do line integral over c, and then maybe your scalar function would be f of x, y, z, and then a fourth variable or something? Yes? But we stop here. We stop where we are. And now we're ready to transition to something completely different. Not completely, but very different. Different enough for me to want to be able to help you understand right now we are shifting gears significantly right now. We're still in the same section though, all right? So we're now going to do line integrals over vector fields. We've been doing line integrals over curves, haven't we? Like there have been curves on the ground. Now we're going to do line integrals over vector fields, which is very weird because a vector field is like the entire space has a vector field in it. How do we do a line integral over a vector field? All right, so we have to go back and we have to talk about some things from physics to help us try and understand what's going on. So back in chapter 10, section 3, we actually talked in this class about defining this thing called work. And we said work is your force vector dotted with your displacement vector. And I showed you this picture of force and displacement. And if you take two vectors and dot them, you can figure out the work done, right? So what we want to imagine now is imagine that we have a point moving along some curve. And we're going to start in two-dimensional space. And let me reevaluate this real quick. All right, so imagine we have some point that's moving along a curve in two-dimensional space. So let's see it right here. You see this point right here, this black point? We are going to be moving that point. Nope, not that one. Sorry. Ignore that. Where's my... No. Where's my move? It's got to be this one. There it is. Okay. All right, so we have a point moving through space, right? Moving through space. Now that curve C is the same curve as before, right? It's the same curve as before. But before we imagined that there was this surface above it, right? And we were dropping a curtain down to this curve. Throw that out the door. That's not what we're doing, okay? We're not going to try that anymore. We're going to do something different. We're going to imagine that as we're moving this point through this space, there is a vector field around us at all times, right? There's some vector field. And so what we want to do here is imagine that that vector field is a force field, some sort of force, gravitational or electromagnetic. Then what we can do is we can look at the total work that is done by this field by adding up the work done at each point as we move along the curve. So if I'm moving along this curve, back it up right there. Okay, if I move along this curve, I'm sorry that the colors are so, there we go, get all that crap out of there. All right, so what we've got here is the point is moving, and just so you know that we're going like this, okay? That's the direction we're moving. So what you see here first is this green vector, which is the capital T, which is the tangent. Do you remember what that was? It was the tangent vector to the curve, but it was capital T is the unit tangent vector. Good. So you have to imagine there's a tangent vector, right? For every point that this black dot is moving along the curve, there's a tangent vector. If we find capital T, that'll be the tangent vector that has a unit length, right? So look at that tangent vector, right? And then this red vector is the field, all right? At that point, that's the field. So if I look at this as a force, right? That's my force vector. And then I need to come up with some vector here, which is like my displacement vector. Then if I dot the two together, I will get the work done moving along that displacement, right? Yeah? Now the displacement